Dear students, this is the lecture 7 and we are going to cover up Carnot cycle today. So the Carnot cycle was proposed by Sadi Carnot in 1824. So again, you see 200 years back. And it is the most efficient heat engine ever proposed. So it becomes the theoretical upper limit for any compression. If you're developing any heat engine, this becomes the upper limit. This is the maximum efficiency that we can ever achieve. And this has been possible because all the processes that Carnot used in his cycle, the Carnot cycle, are reversible process. Means there is no entropy generation anywhere. And that is the reason it became the most efficient, or you can say uh, the best engine or cycle ever possible. Right? Though practically it is not possible to manufacture, but we can always try to achieve near to the Carnot cycle. Now, the Carnot cycle, it basically consists of four reversible processes: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. So this is the PV and TS diagram, but we'll try to recreate it on our own, right? We'll try to draw it on our own so that we are confident with our, at least the TS diagram, we'll try to draw it on our own so that we can be very, very confident with this, right? So what are the different processes? Let me draw the TS diagram here. Right, let me draw the TS diagram. So on the y-axis, I'm representing temperature, and on the x-axis, I'm representing the entropy. Let me say the system initially was at point 1. So from 1 to 2, it is isothermal heat addition. Obviously, if it is a cycle, if it is an engine, we will always have to add heat first, right? So the process goes from 1 to 2 and it is isothermal. And what is the meaning of isothermal? Temperature is constant. Let me say the temperature is the TH, a higher temperature, right? And from 1.1 it reaches 0.2. So this is the heat addition process, isothermal heat addition. And then we go for a isentropic expansion. What is isentropic? Isentropic expansion is nothing else but reversible adiabatic process. If it is adiabatic process, there is no heat transfer. No heat transfer means no energy transfer. If it is a reversible process, there is no heat generation. So the entropy change for an um, isentropic adiabatic reversible adiabatic process will be 0. That is nothing else but known as an isentropic process. So in this process, the expansion takes place. And then what happens is that we go from, this is the point 3, we are in stage 3, then we go from 3 to 1. Now this is the heat rejection, right? From 3 to 1, we are rejecting heat, isothermal heat rejection at a constant temperature. And then from 4 to 1, we have compression process, isentropic compression. We have what is known as isentropic compression. So there are four things that are happening. Just try to see this. We are supplying heat here, heat supplied. Okay? Then this cycle, there will be an expansion device like turbine, right, which will be producing some amount of work here. This is the work output. Then it is rejecting some amount of heat. This is the heat rejected. Okay? Then uh, again, we have to do the compression process. So there might be a pump or a compressor here, and which will require some amount of work. So this is the basic TS diagram of a Carnot cycle. Having understood this, let us try to understand why is the efficiency of a Carnot cycle the maximum. First of all the processes are reversible, right? Reversible process means there is no energy dissipated in irreversibilities, right? Secondly, you see, we are adding heat at an isothermal condition and we are rejecting it at an isothermal condition, and this gives us the best efficiency, right? This gives us the best efficiency. Practically, you imagine it is not very possible, right, to do that unless and until there is a phase change involved. For example, in Rankine cycle, you'll see later on, isothermal heat addition is not a very easy process. If you're adding heat for gas, right, is going to expand. The temperature is going to expand, increase. It is a very, very difficult process. And what you'll have to do, it will be a very, very quasi-static process. And that is how you can achieve this. So practically, it is very, very difficult, or you can say impossible. Uh, but we'll always try to achieve this, right? Now, looking at the cycle, can you tell me what is the total heat supplied? Can I say the total heat supplied is nothing else but the area under the curve process 1, 2? So this is going to be the total heat supplied, right? So let me say this is the total change in entropy, delta S. This is the total change in entropy is delta S, right? So I can say the total heat supplied in this process is equal to TH, that is higher temperature, multiplied by delta S, right? Can you say what is the heat rejected, total heat rejected? Total heat rejected is again TL into delta S, right? The lower temperature, this is the higher, this is the lower temperature, and this is the higher temperature. So higher temperature, lower temperature, where it is heat being rejected. Now you see delta S is same for both the heat addition and heat rejection process. So if you simply divide heat supplied by heat rejected, right? If you simply divide heat supplied by heat rejected, you will notice that delta S is common for both. So it is simply the ratio of higher temperature and lower temperature. This is what Carnot cycles. This is how Carnot cycle helps us. We get to know that if the processes are reversible, then the supply, that ratio of the heat supplied to heat rejected is equal to the ratio of the higher temperature and lower temperature, right? Having said that, it is going to help us define the efficiency of Carnot engine or any reversible engine. But before getting into an engine, let us see what are the conclusions of Carnot cycle. So there are two principles that can be derived from Carnot cycle. The first being that the efficiency of an irreversible heat engine is always less that of an reversible heat engine operating between the same two reservoirs. Same two reservoirs means same higher temperature and lower temperature for both the engines being same, right? And we know it, right? We know obviously the efficiency of a reversible engine will be greater than that of a irreversible engine. We already know it from our last lecture, right? From the entropy lecture of the second law of thermodynamics, because in irreversible engines some amount of energy will be dissipated in form of irreversibilities like friction, right, which will result in generation of entropy. And so definitely this is something true, right? So if you really want to build an efficient engine, we should try to build a reversible engine. I know that this is not a very feasible task, but we should always try to achieve the best. Secondly, the second principle says that all reversible heat engines operating between the same two temperatures have the same efficiency regardless of the working fluid. This is something interesting. What he's saying, if all the reversible heat engines operating between the same two temperatures have the same efficiency regardless of working fluid. Huh? Means working fluid does not matter. You are using air or you are using, say, uh, some other kind of gas like helium or you are using water. It does not matter. Let us see how. Right? Now, efficiency of a reversible engine. How can we represent efficiency? We have seen it in our heat engine. We have done a class on heat engine, right? So we know it is efficiency is the work output by the heat supplied, right? And work output can be given by first law of thermodynamics, heat supplied minus heat rejected divided by heat supplied, right? So this is equal to 1 minus heat rejected by heat supplied. Now we have already seen that the ratio of heat rejected by heat supplied can be written as 1 minus T lower divided by T higher. So you see the efficiency of a reversible engine, right? It this is the maximum efficiency of a reversible engine, that is TH by TL. So you see it only depends on the higher and lower temperature. right? So this is the maximum efficiency that can be reached. This is the maximum efficiency, or better to say, this is also known as the Carnot efficiency. Carnot efficiency, or efficiency of a Carnot engine, or you can simply say efficiency of a Carnot engine. So this is the maximum efficiency a reversible engine can reach, right? No doubt we might not be able to have the exact efficiency. So you can say any efficiency of an irreversible cycle, right, will be always less than, right, the efficiency of a reversible cycle. So we now have a maximum limit of efficiency and we should always try to achieve it. Having said that, what about reversible refrigerators and heat pump? Now, if you want to see the COP, if you remember COP of a heat pump, let us take the refrigerator first. COP of a refrigerator is the desired effect divided by work input, right? And what is the desired effect? It is how much heat has been absorbed from the lower temperature source, right? And divided by work input. Work input can be written as total heat rejected at the higher temperature minus total heat absorbed from the lower temperature. So this becomes, if you see the ratio, right, you can again invert it and you can use the ratio. So if you simply replace it with the temperatures, it simply becomes TL divided by T higher minus T lower. We can always change it. Okay, we can take the inverse, then get the ratio and supply temperature. It can be proved, not a problem. So this is how you can write the COP of a refrigerator. Similarly, COP of a heat pump. How can you write the COP of a heat pump? COP of a heat pump can be written as Q. Desired effect is QH. Right, work input is going to be same. How much heat is being supplied to the higher temperature, and how much minus how much heat has been absorbed from the lower temperature. So this can again be written as T higher divided by T higher minus T lower. And if you try to see this, the COP of a, if you try to compare the COP of a heat pump and refrigerator, you'll see that the COP of a heat pump is going to be COP of a refrigerator plus 1. So we have understood the Carnot cycle and how it helps us, right, to find out the maximum efficiency of a heat engine and the maximum coefficient of performance COP of a heat pump and a refrigerator. Thank you, class.